Hi, everybody, and welcome to maybe our first live stream here on the Aqua Open Source YouTube channel. It's so great that you're joining us here. For those who are watching right now live or joining the recording later on, it's really great to have you. Maybe say hi in the comment section. We see all of your comments, so just say hi if you're here, maybe where you're joining us from. And yeah, then we're gonna get started. I have three amazing people here from the Aqua Open Source team. I'm just going to bring them on one by one. But let me maybe introduce myself first. So I joined the Aqua Open Source team just a few weeks ago as their developer advocate. And it's really great to host these live sessions to allow you to come join us, hear about the tools, related technologies, and ask your questions. So yeah, just say hi in the comments. Let us know that you're here, that you can hear us. If there are any technical issues, anything like the audio is too loud or too quiet, or you can't see the screen, then please do let us know in the comments as well. I think you have to be subscribed to our YouTube channel to be able to comment. So make sure you subscribe, and then you should be able to go ahead and comment. I might turn it off during the live stream. We'll see how that goes. But yeah, let's say hi to everybody else who's going to join me on this live stream. First, we have Raphael. Hi, Raphael. Hi, how are you doing?
Hello, all good. Thank you.
Awesome. You want to let us know who you are and what you do at Aqua?
Yes, I work in the open source team and I'm currently one of the maintainers of Tracee, together with other members of our team.
Awesome. Maybe let us know one fun fact about you. Hobby. How you got into
computers.
tech? Computers.
Yeah.
Everything about computers.
Yes, unfortunately.
It's a good thing. Awesome. So next up, we have Grant.
Hello.
I feel like in a talk show, you know?
Yeah. Thanks for having me.
Amazing. Hi, welcome. Awesome. Is this your first time on like a live stream on the Aqua YouTube channel?
On the Aqua channel, yeah, I think so.
Awesome. I hope I'm gonna make this a memorable experience with the help of everybody watching here right now. Awesome.
I'm sure we will.
Do you want to give us like a quick overview of who you are and what you do at Aqua, and one fun fact?
Sure. So yeah, very similar to Raphael. I'm on the open source team at Aqua, and I'm one of the maintainers of Tracee, as well as libbpf go. And let's see, a fun fact about me is I'm very into cycling.
Very into cycling.
Yeah.
Awesome.
My bike.
How often do you cycle? It's right there, your best buddy. Awesome.
Every day if I can.
Every day.
Weather permitting.
Awesome. So we have some people in the chat. Yeah, so you have to wait. Hi, Engin. Thank you so much for joining. I hope your team is joining as well. You have to subscribe to the YouTube channel and then wait 1 minute, and then you can post in the chat. Just 1 minute wait time, and then you can join us in the chat and comment and post your questions related to Aqua, the open source team, and also Tracee and ebpf, which we're going to dive into in a second. Hi, Carol. Awesome. Thank you so much for joining. Hi there. It's great to see so many people. And now we have Itai. Hi.
Hi. I was afraid you were going to forget me. Hello, everyone. I'm Itai Shakuri. I lead the open source team in Aqua Security, where we build a lot of cool open source cloud native security stuff.
Let us know one fun fact about you, about your life, your hobbies.
You should have prepared me for this.
No, that's what I do this, to put you on the spot, like something unique.
I don't know if it's unique, but I like to start every morning with a yoga exercise.
Oh, I didn't know that.
Yeah.
Awesome.
Now you know.
Yeah. Is it a big thing in Israel, yoga, or not?
Maybe.
In your life it is.
For me it is.
Okay.
Yeah.
Awesome. Cool. Yeah. So we have people who do yoga, who bike. Awesome. So we are gonna get started talking about ebpf and Tracee then. So you have a little. Who wants to get started?
We could start with the demo, or we can start with talking about ebpf. What do you think would be more the best order? Maybe start talking about ebpf first?
Maybe let's start talking about, give a little bit of context of what ebpf is, why you would want to learn about it, who uses it, some use cases, and then from there we can go to Tracee. Sounds good?
Cool. Yeah. Rafael, you want to get started?
Rafael, what is ebpf?
ebpf is a lightweight way for you to introspect into Linux kernel and to get information out of it the way you want to have it, like in a programmable way. So in short terms.
Okay. Why would I want to get information out of the Linux kernel?
Well, there are some kind of programs that need to interact with kernel, right? So those programs that needed you to create kernel modules to do so and things like that now can rely in just a program made and loaded into the kernel in an easier way, at least for the user, maybe not for the programmer, but it doesn't require environment changes, and you can just load a simple program into the kernel, get things you need out of it, and a very good communication in between the kernel and userland, which is a tool that's running in the operating system. So that's why you would like to use it, in my opinion, I think. Maybe I'm not forgetting anything.
So the cool thing is like loading the program into the kernel, which is like there's different ways to it, and ebpf makes it easy and safe and fast, and I think this is what's cool about it.
Yeah, and it's a safe way as well. Like in the other techniques that we had to introspect kernel or to act inside the kernel, we were very close to breaking the kernel and the way it is supposed to work. And BPF has lots of safe measures for us not to break the kernel, but yet be able to either introspect or tell the kernel to do something.
So without ebpf, I have to make changes directly to programs running within the kernel that are part of it. Correct me if I'm saying anything wrong, right? And that's potentially dangerous, and I can break lots of things that I don't want to break. And ebpf allows me to programmatically interact between the user space and the kernel space and get information in and out without actually having to make hard changes. Can I say that?
Yes. So what it actually looks like is just writing small programs, sometimes only a few lines, but small programs that attach to different points within the kernel. So you could attach it to a system call so that every time a system call is executed, your BPF program would be run in response to it. Or you could attach it to a network socket, or you could attach it to like a whole bunch of different networking things. Like there's a lot of network use cases, but also like system tracing use cases. Like you could attach them to LSM hooks and all these different things. And yeah, there's a lot of restrictions on what you can do with it, which is means that there's workarounds that you have to do if you want to get all the information you want or do all the things you want, but it also leads to a much safer way of collecting information that you want.
So there are restrictions to ebpf on how I can interact with the kernel.
Essentially, yes. Like in your actual code, you have to. There's a limit on the amount of instructions. Like all ebpf programs have to terminate. Like you can't just have a BPF program that's just running forever. And there's limits to the memory that each BPF program, depending on what type it is, what memory it could access, things like that.
Could you maybe, when I share your screen, and provide us an overview of where does, like in our tech stack, let's say I'm a full stack developer, I know kind of different interactions between different areas of my system, right? But I don't actually know where ebpf fits in, right? Can you maybe give us an overview of that? Of I know I asked you to create some drawings live. Do you want to do it, Itai? Can I share your screen?
Yeah, I think Rafael wanted to do it. Or I don't want to
You
call you
want
out,
to do
but
it?
only if you want to.
No, go ahead,
We
Itai.
can
I
tell you
think,
what to
yeah.
draw as well.
All right. So
I give you a second.
yeah, give me a
to
second.
to bring up the screen, and then also, so if you're just joining us, you need to subscribe to the Aqua open source YouTube channel, and then after 1 minute you can ask away all your questions in the chat. Ask any questions. I'm asking super basic questions. Super basic questions. I'm asking all the questions that come to my mind right now, so feel free to just drop the questions in there. I see that we already have a question from Engin, which I'm going to address later once we're going to look into more detail on Tracee. So right now we're just going to explore ebpf and why we would use it, and then we're gonna dive into Tracee afterwards. Awesome. Say hi in the chat. Hello there. Thank you so much for joining. So Itai, can I share your screen?
Yes,
1
it's
second.
currently just a
Yeah.
black canvas.
Okay. I'm gonna share your screen.
Yeah.
So
All right. So what are we drawing today?
maybe provide us
yeah,
with an overview of where's the kernel, where's our application, like
yeah.
to provide
So
really high level context. What
some
is it we're talking about?
fundamentals. Yeah, some fundamentals. First of all, there is a boundary between your application, whatever it's going to be, your web server, your laptop, whatever is running on it, your servers in the cloud, wherever it is. This is your application, and your application needs to do stuff with the operating system, whatever it may be. We're in a Linux world. This is where Tracee thrives. So for us, this is actually Linux. And the interaction goes that if the application wants to do something with the world, like read a file, call a service, write to the screen, anything it wants to do, anything it wants to access from the actual computer that it's running on, it needs to ask nicely from the, let's call this the kernel. And this interaction is usually, not exclusively, but usually done using a system call. Let's call this syscall. It's basically the application wants to, for example, open a file. It will ask the kernel, who governs all the resources, all the hardware, to open the file, and then the kernel, using device drivers or whatever, will actually fulfill this request. This is one fundamental thing that we need to understand before we talk about tracing with Tracee. And another thing, well, actually, inside of the kernel, there's a lot of things going on, obviously. Where does ebpf fit in? So let's say that, so inside of the kernel, let's expand this actually. Let's do this like this. So inside of the kernel, let's say that you wanted to open something. There is like a flow of things that is happening. We need to check who you are. We need to find the file. We need to resolve it. We need to ask the disk to find it. We need to copy the bytes from here to there. We need to do a lot of different things in order for it to happen. And eventually you get your result. But for our intentions, every one of these steps might be a place where we want to inspect, where we want to observe what is happening. There are different mechanisms to do that, but the nice thing about ebpf is that it allows us to attach different lifecycle events in this process. I'm using open for an example, right? But it could be anything. Lifecycle events in this process, and basically, let's say that this is a program. We inject our program, our ebpf program, into the kernel, so that, let's say we were particularly interested in this step. So now this step, okay. So now this step, we have a chance to intercept it, and then inside of our ebpf program, let's say that we want to find out what is the inode of the file that is being opened. This is our code. This is code. So we wrote it. We could do whatever we want with it, and in this case, we can send it out to our own agent here, which we will call, for that matter, Tracee, but it could be any basically user space ebpf driver. And this is the high-level flow of things.
Awesome. So question for me, when I'm creating an application, I usually don't have to know how my requests or like my different, the things that I want to do within the application are processed within the kernel space, right? I don't
Yes.
know that. How much do I have to know when I'm using, for example, Tracee or other ebpf programs? How much do I have to know about how it's processed within the kernel, right? Because as a developer, I usually don't really know what's happening there, right?
Yeah. So I'm going to show maybe a demo soon, and then I will show that you can interact with Tracee in two ways. One is that if you want it to just trace everything that's happening, and then you can take a look with your eyes and investigate the raw data. In this case, you want to know what's happening to some level because you want to know what you're looking for, but also Tracee helps you abstract away some unnecessary complexity, and I'll show you how in a second. But the better answer is that if you just want to detect bad stuff that might be happening, then you don't really need to parse through all the raw data. You just need to run Tracee, which comes with a bunch of, we call them signatures, which is basically patterns and rules that we know that we want to look for because we have identified them as suspicious, and they codify the suspicious behavior. So as a user of Tracee, you don't really need to know anything about how the suspicious behavior is detected. And by the way, we haven't introduced Tracee and said that it is
We're gonna go there in a second. Let's go to Tracee in a second.
Yeah.
Is there anything else that Raphael or Grant want to add to ebpf, like use cases? Overall, high-level use cases. Not what Tracee is used for, but what are high-level use cases for ebpf right now?
Yeah, so we talked about tracing also in the way that we introduced ebpf. ebpf could be used for other stuff. So I like the analogy that ebpf is like ebpf to Linux is like JavaScript to the browser. It basically allows you to extend the kernel and to run your code in there. And different subsystems of Linux are now changing to be able to accept and to leverage ebpf programs. So we talked about observability. There are different use cases. For example, another big use case is network programming. So you could completely manipulate the flow of a packet, or even like implement things like a load balancer or things like that completely in ebpf. So that means that the code, your business logic is executed in the kernel, and it's a lot more efficient. And this is another use case. We see ebpf going into IO use cases, like disk use cases, permissions, like this, making decisions based on permissions, many different use cases.
So you mentioned two things here. One of them is that ebpf right now you can use it for some parts of the kernel, but not for everything. Did you mention that?
Yeah, I mean, the kernel is C code, and whoever writes a certain subsystem in the kernel can decide if they want to accept, basically, if they want to allow extending their subsystem, and if so, if they want to do it using ebpf. Most probably they would want to do it today with ebpf, but not every little piece of the kernel is extensible. Today, it's going the direction though.
I think there is one important thing to mention, which is the BPF is kind of a revolution for some stuff, you know. So we are touching the parts where it's good for introspection, which is something that Tracee does and takes decisions based on it is introspecting, and also about data planes, you know. So in the last years, some projects, or maybe lots of projects, try to bring all the data to userland directly, so they could use their own network stacks into, you know, a specific data plane and process packets faster and things like that. So there is an entire world in BPF related to data planes and packets processing and packets mangling, changing packets and directing packets to other hosts and things like that. This is like one part of BPF, which is very used. Then we have like the introspection thing, which is like I would put as a second thing. And then the third thing would be taking actions inside the kernel, which is like, for example, what Itai was saying, we can plug into security parts of the kernel and allow or disallow something to happen. So I would divide the BPF world into at least those three major pictures. Not sure if the Itai and Grant agrees, but that's how I see nowadays.
I would add that in addition to thinking about like what information you could actually get from the ebpf code, there's also, you know, once you have the data coming out, you know, you have the data of what's happening in your operating system, then the use cases for that are also endless. So, you know, let's say you have tracing programs like with Tracee, for example. We have these BPF programs that are collecting information about all these different events, all these system calls, file events, network events, and I guess Aqua's use case for this is, of course, security. So we have Tracee rules to build policy on top of that for detecting when, you know, there's some type of malware or some type of intrusion happening. But hypothetically, you could also use that data from Tracee. You know, Tracee is just the engine. You can use that data for any type of performance monitoring or logging or observability for the sake of you know, checking on availability and things like that. You know, there's also you know, another example is like BPF has access to attached to U probes. So in your actual application that you're running, your own custom workload, you can attach to functions in those actual programs. So that could be useful for debugging. So you might want to use that information to say, like, how come this function is not getting called, or what are the parameters that are being passed to this? Is the data being corrupted somewhere? But that also can be interesting for security purposes, because you could say, like, when is this sensitive libc function being called? Or yeah, there's just quite a lot of possibilities. And I'll also add that there are on the BPF mailing list, there's very often new proposals for different BPF program places to it, or places to attach BPF programs to. Like one that's always discussed is attaching to the scheduler and having BPF programs that you can custom write rules into the actual Linux scheduler. Yeah, there's quite a lot of possibilities. It's exciting.
Awesome. That's a great overview. Do we want to dive into Tracee now and focus more on Tracee as a use case and how to use it? I think Itai, you have to share your screen again.
Yep.
In the meantime, if you're joining right now, you have to subscribe and be subscribed for 1 minute, and then you can go ahead and join us in the chat and ask your questions. We already have lots of questions, and we're gonna dive into them after we've seen the Tracee demo. And yeah, so let us know in the chat if you have any questions, anything regarding ebpf, Tracee, Aqua open source. Awesome. Also say hi in the chat. Let us know that you're here. And
so before I share my screen for the demo, I just want to quickly share just where to get Tracee if we're introducing it.
I'm going to share your screen, yeah?
Yeah, can we?
Yes. Here we go.
All right. So this is Tracee on GitHub, github.com/aquasecurity/Tracee. Let me make it bigger, actually. Okay. And basically, this is where everything happens, all the magic happens. And I just want to point out that Tracee is fully open source. It's here on GitHub. There is a quickly getting started guide and everything. I will walk through it now. Also the documentation, which you can quickly access through here. Oh, you jumped to another tab. Let's do this. The documentation where you can, again, get started, understand how it works, how to build it, how to run it in different environments, on different flavors of Linux, in Kubernetes, how to integrate it with your tools of choice, about rules, which I very briefly mentioned. So everything is here, just so you have it in the back of your minds if you want to go and check out the documentation later. All right, so now I will share this, and we can start looking at Tracee. Can we see my screen?
Yes.
All right.
Should be able to. Can you make it a little bit bigger for those people who are watching on their smartphones?
It's already quite big. Okay, I think this is big. Okay. I'm going to run Tracee. First of all, like this. What do we see here? Docker run is basically a container. It's called aquasec/Tracee. The latest release is 0.6.5. And you can basically copy this straight out of the README or the documentation. It's just some boilerplate. And when you run Tracee, just the container like this, what will happen is that it starts detecting stuff. It loaded some signatures. I mentioned those signatures are basically the codified patterns that Tracee will be looking for. And we have a few of those shipped with Tracee. You can also extend and write your own, which maybe we'll get to that later. But basically, this is a very quick way to get started. But before we look into the output of that, I want to show you what happens behind the scenes. So I will run Tracee again. This time I will start the trace subcommand. Okay, actually, let's close it because a lot of things are happening right now. It basically dumps all of the things that it can gather that are happening right now on my computer, which is a lot of things. You can see when something happens, the user who made it, the command, the process IDs. This is the interesting part, the event itself. There are different kinds of events that we trace, and the arguments of the events. For example, there's a lot of file opening happening here. And you can see like someone tried to check capabilities, someone closed this file, a lot of things happening here. If you want to get the complete list of events, you can do this list. And you see these huge tables of all the events that Tracee can trace for you. This is something cool to mention, that Tracee can trace all the system calls right out of the box. You don't, like, there's no coverage map that we're trying to fill. Everything is already there. And moreover, in addition to system calls, the first table is the system calls. Then there is another table of additional events that we've added on top of system calls that allows us to look into more depth into what's happening. And I will give you one example of this now. So I want to start tracing again, and I want to, on this lower terminal, I want to run this small program, I love cats, and I run it, and it meows. So this is my program, and let's say I'm running this in production. This powers my business, and I'm running this in production. And then I heard at some live stream that I should look into runtime security. So I also start looking into what's happening behind the scenes on my server. So we saw that if we just run Tracee like this, we just the trace subcommand, it will just dump everything that's happening, but that's too much information to consume. So I will help it a little bit by using the trace flag. So I can tell it for specific things that I want to trace. This is the help. I did a trace help just for it to show me what kind of filters I can apply here. And there's a lot of stuff. Basically, everything you see here is filterable. So, for example, UID PID, mount namespaces, PID namespace, what kind of events, what kind of command, which container it came from. A lot of things you can filter for. You can see some examples here for show me only things coming from a new process. So show me only things coming from this specific process. Show me things from this process tree, things with certain kind of users, and so on. To help us, we'll use this filter, which focuses the trace on a specific command. So I'll do com equals of cats. This is the name of the command that we'll filter for. By the way, we can combine. We can add another trace here and then further limit the result set. I'm going to run this now. And I run my program again and stop Tracee. And I see what it did. So what do we have here? Let's we have some boilerplate here, which we're not going to get into. But something interesting that happened is that on top of just writing meow, we saw that it tried to open this very secret file on my server, which is not good. And I didn't know that it's doing that. It didn't tell me that it's doing that. So this is the first step of how observability and system tracing can help me understand what's happening. And now I want to show, this is something that any system tracer can help you detect, even built-in tools in Linux, better tools or worse tools. It's a pretty basic functionality. Now let's see how Tracee takes these kind of things, and just by one example out of, I don't know how many, something that Tracee can help you with. So you can see this path name. By the way, this is the open@. Open@ system call. Let's quickly take a look at it. Let's see what is open@. You can open. You can give it. Sorry, I'm looking at this one. You can give it the path name, some flags, and this dirfd. And we also saw this here. This is the dirfd. This is the path name. These are the flags. And you would notice that this path is relative. While I'm running this on my servers and collecting all of this information, I will probably not know what this is relative to. And if I consult the documentation, I will see that, let's search, for example, for this. So we can see some pretty sophisticated business logic in different cases. If path name is absolute, then DRFD is ignored. If path name is relative, DRFD is, and DRFD is this special thing, then it means something. If path name is relative and DRFD is meaningful, then it's relative to DRFD. So I will need to now start investigating, based on the output that Tracee gave me, what is this actual file? So according to the documentation, I will see that DRFD is provided. So my secret file is relative to 3. Well, 3 is the file descriptor. This is a FD file descriptor. So how do I know what is this third file descriptor of the process I love cats? I can like do I don't know. I could do something like lsoff or something like that, and try to investigate this. Probably by the time that I'm going to look into it, the process will be long gone, so that won't be helpful. I can also look back in the trace log and see that sometime earlier, something opened this path and received the file descriptor 3. So 3 is actually this thing, and I could trace back through what's actually happening. Or Tracee can help me, and you can see that it also gave me, in addition to the openet system call, this companion event that is called security file open, that in this case gives me the fully absolute resolved path to the file, regardless of how it was invoked. We also saw that open has different flavors. Open like this, create can also open, open@ is something else, open@ 2. I don't know. This is actually, Anais, what you asked earlier. I don't know what the program actually does. I know maybe that I'm looking for opening of files, maybe even not that, but maybe I know that I'm looking at opening of files, but I don't know how the code was written. Actually, in most cases, the developer will not know even how the lower level libraries would choose to open the file. So in this case, this is a very helpful thing that Tracee helps me by telling me, you don't care how, but this file was opened. And this is always going to be the fully resolved and correct path, even if this was a symlink, even if this was a file descriptor. So this is very helpful. And this was just anecdotal example. There are many different cases where you want to look at the file that was executed, or you want to look at other stuff that are happening. The Tracee supplement the system call raw data with some more useful information. I'm going to pause for a second for questions or something.
You're muted, nice.
I was saying, don't stop sharing your screen. Let's get to some of the questions. There are lots. I know that some already got answered in the chat, but it might be helpful, like especially for the people who are watching the recording, if we can just iterate on it, on the answers right now. So one of them here, thank you for joining, Vaishali. I hope I pronounced your name right. So is asking, hello, thanks for the live demo. Just curious question. I see that Tracee uses libpf. BPF, go. Are there any historic specific reasons for not using Cilium ebpf? Who wants to take that?
I can answer that. So originally, when Tracee was being built in Go, I guess the original version was in Python, but when the original version was being built in Go, we saw libppf was quite an exciting thing that was coming out. So there was a combination of wanting to adhere to this standard that libppf is being built as the standard library for an implementation of a user space library, as well as the Cilium ebpf package. One didn't support kprobes at the time. I think it does have some support, or perhaps fully supports it now, but not not in the first few months of Tracee's life, as well as even now when we have tested it and explored it, and it's not quite built for tracing projects. It seems to be better for the use case of networking.
That is Cilium eBPF.
Correct. It's an interesting trade-off between, we're of course shelling into like using Sego, using I guess not necessarily shelling, but using Sego to call into libbpf, whereas the Cilium eBPF library is like natively in Go.
There's also something that we mentioned in last Bloomberg's conference, and that was that we wanted to reuse fast whatever the kernel engineers create. libbpf is currently being developed in the kernel together with responsible for other parts of the kernel. So as soon as they add a feature, for us it's very easy to implement that feature as long as libbpf supports with kernel's direction, which is not necessarily true for if you are implementing things by yourself, which is, in my opinion, the case of Cilium eBPF. They're probably implementing things that libbpf already has. So it's easier for us to reuse. It's like not reinventing the wheel for us, and then we can concentrate into specific problems. One of the examples I have was we needed to support LTS versions, and upstream libbpf did not support having external BTF files to support those kernels that don't have that. It's basically like having the embedded information in the kernel about symbols and types being used, etc. So some of the LTS versions, Linux LTS versions, did not have that information. So we generated all the information from all the existing kernels, and we made libbpf to support that. So now all the community can benefit from it, and other projects started using it, So it's like we are trying to create an ecosystem, but together with what is being developed.
Awesome. I was thinking of the screen you showed me on GitHub with all the supported kernel versions. So that might be interesting to show, actually. I found it was interesting. So should we move on to the next question? Good. We have here a question that is asking, thank you for joining, Arthur. So what are the main differences between Tracee and Falco? Itai, do you want to?
Yeah. So first of all, it's a fair comparison. Both are runtime security open source solutions. There are some differences. One is that, first of all, there's the system call coverage, which I talked about, and also the additional events that I gave you just a sneak peek into. Also, actually, some of the things that I want to answer, I'm going to demonstrate soon. So maybe we can keep this question to the end, and then it will be better to answer it then.
So you want to show it like it's part of the demo?
Yeah.
Okay, so let's keep this question to the end. Let's go to the next question. There was one early on at the beginning that got also answered in the chat by Engin, which is asking, we use Phantom OS. Are we able to use Tracee? I know the header stuff is always tricky. Could you provide more context on what is the tricky header stuff that he's referring to, and why is there this concern that he might not be able to use it? And can you use it? In simple terms.
Maybe this is a general question about the requirements of Tracee. What is required to run Tracee?
Yeah.
You need a BPF capable kernel. And by the way, we say eBPF and BPF interchangeably sometimes, so apologies for that. And you like the easiest way to run Tracee is if you have a modern kernel which is BTF enabled. Rafael said something about it just a second ago. Maybe you want to explain more what it means. But basically, in order to make in order to make ebpf applications portable between operating systems, we use this feature that is called BPF, which stands for BTF stands for BPF type format, and it's fairly new. So you may want to have a kernel that already supports that. That would be easier. If not, we have a solution for that. And besides that, I don't think there are any other significant requirements. And now, Rafael, maybe if you want to say something about the portability.
Yes, the question was Phantom OS, which is another operating system, and then it was corrected to, I think, Photon OS, which is like a VMware container image, which, as long as the kernel supports BTF, then we can run on it without having to compile Tracee. Tracee is distributed in two ways. It's like a slim version and a bigger version. So in order to have Tracee not to have to compile itself during runtime, you want to execute in kernels that support BTF or in kernels supported by one of our projects, which is called BTF Hub. I'll give just a quick example. For example, Ubuntu Bionic and Ubuntu Focal did not have support for embedded BTF information in the past kernels for the LTS versions. Now they do after we worked with them, so they could enable that. But then we have support for those kernels that did not have that information through this BTF Hub project. For other Linux kernels, you can either opt to provide support for those within the BTF Hub project, or if they are using a recent enough kernel, then the BTF information is already embedded in the kernel, and then you can just run the BPF without needing to compile anything. So it's kind of this.
And maybe I will just summarize by saying that we are working towards a fully portable version of Tracee, which we don't have to worry about anything we just said. And I really hope that soon enough we can. This is actually part of the README now. If you look at the README, then you see that we tell you if you're running on BTF enabled kernel, you run it like this. This is the easy way. This is how you detect if you're running on a BTF enabled kernel, and if not, you do it like this. I really hope you can just remove all of this from the README at some point and just tell you to Docker run Tracee. And I think we're very close to that.
Awesome. Let's see. Do we have other questions here? You wanted to dive into the Falco question.
Let's talk about the actually running Tracee. So far, we haven't run Tracee. The main use case, we have actually traced specific things. So I want to show, first of all, what does it feel like to run Tracee? May I?
Yeah, go ahead.
I don't see you, so I can only hear you.
Can you hear me? Okay, go ahead. You have my go.
All right. So I'm gonna do now something something similar. I'm running the same thing. Now I don't specify any subcommand, just Docker run Tracee essentially, and it will start running. It will still collect all of this raw data, but it will not show you it because you don't care about it. You only care about suspicious things that are happening. So I'm going to run it, and I also I have here other tests, some tests. So we have signatures in Tracee, few shipped into Tracee, and this is triggering some of the signatures. So this test, for example, is triggering TRC2. Let's see how it looks like. I'm going to run Tracee. I'm going to go here to let's move this here. I'm going to go to tests, and let's run TRC2. This is the idea of the signature. Doesn't really matter for now. It did something, and you can see here that a detection was made, and that TRC2 is actually anti-debugging. It's a specific technique we call evasion technique that some attackers might use to hide themselves, and we think this is kind of suspicious, so we let you know about it. And this is how a detection looks like. Let's look at another detection. Let's do something else. Let's go here. I have here this.
I accidentally
very
removed
cool.
the screen. Yeah, here we go.
Again, sorry.
Go for it.
Okay. I have here this a nice utility that I like. I didn't write it. I found it on GitHub. Apologies now because I don't remember who wrote it. Maybe I can give credit very quickly somehow. Anyway, it executes a binary, but not directly. It can execute a binary without the binary ever touching the disk. So a lot of anti-malware tools or tools that are looking for actually scanning files will not pick this up because it can execute a file directly from the internet, for example, without ever writing it into disk. So to demonstrate, I'm going to run it, and this is just a Linux kind of tidbit. This tool is just demonstrating it. This tool by itself is not malicious. It's just a tool. It's executing an elf, and I'm telling it to execute. Let's execute ls. Okay, and you would notice that I'm piping ls. Let's do it more clearly. Just a sec. So this is where ls is at, and on elf exec, and I'm passing through standard input another file. Now, the interesting thing here that this could have been just a string or a request from the internet or anything. But for the sake of the demo, I'm just passing in the file. So it's being executed through standard input. And it works. It did execute it. And if I were to trace what is happening using the raw data here, we might have missed some things, like if we wanted to see when a file is being written or something like that. But if I would run Tracee again in detection mode, it would see that not necessarily malicious, but a fileless execution, which is a specific way to execute a binary, which is very peculiar. Why would you want to do it like this? It detected it. So eventually, there are a certain set of possibly suspicious behaviors that Tracee helps you detect, and you basically just get the end result. You usually won't care about the raw data unless you want to further investigate. First, you want to be alerted. So this is how you are alerted. Right now, I'm outputting the alert, just writing it out, but I can also with Tracee send the alert somewhere else, and maybe we can talk about that later. First, I wanted to just show this use case, which is the primary use case of Tracee.
Awesome.
Questions so far?
I don't see any questions.
All right. So one thing I want to add is that these signatures, some of them, and this is a unique aspect of Tracee. I'm now clicking into the signatures folder under Tracee, and you see here Golang and Rego. We can Tracee supports writing signatures either in Go. Tracee itself is written in Go, or in Rego. Rego, for those of you who don't know, is the language behind OPA, the Open Policy Agent. This is a very popular CNCF project that is used for policy enforcement. It's basically a DSL, a domain-specific language, to express policy decisions, criterias. So let's look, for example, at the anti-debugging signatures that we have just seen a demo of. This is TRC2, right? And basically, this is it, just this. Everything else here is metadata. This is what codifies the suspicious behavior. And it's basically saying that if an event of type ptrace is a specific system call in Linux, and if we saw a ptrace where the request of the ptrace is to trace myself, then it's something that we want to, for example, identify. There are different signatures here. Like let's look at the fileless execution, which we also saw a demo of. This is how it's implemented. Actually, we found that there are 3 ways to implement it. So we have expressed them all as a Rego code here. So for example, if we see that a process is executed from a path that starts with memfd, which is the specific Linux capability that allows writing a file into memory without writing it to disk, then this predicate will basically match, and we will alert. And there are different flavors to this, but basically this is how you write the signatures using Rego, which is, I think, pretty cool. And you can also extend the built-in set of signatures with your own, write stuff that you want to detect. Basically, you just create a file, a Rego file like this, and follow a convention that you have to write a Rego rule. This is called a rule. This thing, a Rego rule that is called Tracee match. This is the only convention, and you basically define the criteria here. This is like, think of it like a big if statement. If everything here is true, then there is a match, right? If everything here is true, if the input event name is this, and the path name starts with memfd, all the conditions here evaluate to true, then this is a match. And you can write a lot of cool stuff here thanks to Rego. And this is the second thing that I wanted to mention about Tracee.
Awesome. We have a question at this point, if I can blend it in. So Arthur is asking, signature detection looks awesome, but it looks like it still requires some Linux security knowledge that most developers lack. How do you see beginners using Tracee and slowly improving on this domain?
So yes, if you want to write your own signatures, you do need to know what you're looking for, and this requires specific knowledge in Linux internals. So for the first thing that I would say is that we do ship with a pretty nice set of signatures out of the box for you to just benefit from. So if you're looking for a way to add security to your servers and clusters, just run Tracee and don't worry about it. If you are looking for extending Tracee with your own signatures, then you can start by looking into popular system calls. I think a lot of the common requirements that you would want to enforce using Tracee are basically, you need to know maybe 5 system calls, a handful of system calls. So you can just look at how they look like for example, a process is being executed, a file is being opened, these very common things. And this is a very good way to get started.
Awesome. I hope that answers the question. Let us know if you're looking for specific links to any of the resources that we mentioned right now, any of the parts. Cool.
And I just want to refer back again to the list of all events. And what did I do? Oh, sorry. And you can also refer to this as help, kind of lightweight help. So, for example, you want to look for something that is being executed. So you search for, you see this system call exec ve. So it's a very famous one. So you can see what it might give you. So you can start by looking at what data Tracee gives you, and then think what you can do with it, or you can go the other way around. You can think what you want to look for, and then which system calls might contribute to it, and find them in this list. And to circle back again to the extra events that we provide on top of system calls, these are there's something interesting that I wanted to mention here, is that not only I gave the demo of like the open, when it helps me understand, it helps me resolve the file, or it helps me to not care about which particular flavor of open was used. Actually, everything here that starts with security is part of a Linux security modules infrastructure. It's basically a part of Linux which we will not get into at the moment, but the fact that we hook into the LSM events helps you in a few ways. First of all, you have a collection of very interesting and very useful, I think, events that are happening here to help you look for interesting stuff on top of system calls. Second of all, they are very consistent. So in the case of open that I gave, or for example, you have dup1, dup2, dup3, the system call interface is ever expanding. So it's a lot more convenient to use just the internal function that will always be triggered with the same name. Also, the information here is more reliable, because as we saw that, for example, the link is resolved, same for the binary, etc. But another interesting point is that it's more secure, because system calls eventually are an interface between the user and the operating system. The user has a way. The user has some control about the input there. So the user might try to leverage that, and there are certain categories of specific attacks that leverage that that attack vector. Without going too much into details, system calls are subject to a certain level of attack that might make them not as reliable, and the security events here are not. So you can also be more confident in using those instead of system calls. Just another point that I wanted to add. By the way, all of this is actually documented in Tracee, and we've written blog posts and content about it as well.
Just blending in the docs. We're just here, and also linked in the chat. And then the Git repository is at aquasecurity/Tracee on GitHub, right? Awesome. Anything else you want to cover?
No, just to circle back to the question about unique things in Tracee. So I think overall we touched a few. the security, the LSM events, the OPA-based rule engine, the portability of Tracee thanks to the BTF support. So if you look into things, you would find certain aspects that are unique to Tracee for now, and might make you want to consider using it. Yeah.
Let me put us back. Awesome. Are there any other questions? I see that Yaniv, who's part of the Aqua team, is jumping in and helping us out, answering questions, providing more details. Awesome. Thank you so much. Yeah, if there are any other questions, please do let us know, either right now, like in the next minutes, or in the comments, or also make sure to join the, let me just put it up. Join the Slack channel where we are available. I want to say around the clock, more or less, since we're in different time zones, but make sure to join the Slack channel as well. Just slack.aquasec.com. That's where you can head over to the Slack channel and just ask any questions that you have there, anything that's unclear, that you're struggling with. You can also ask us directly in GitHub. Just 2 options. And then also make sure to give us a little star on GitHub if you're checking out Tracee, if you're trying it out, seeing how it works, experimenting around with it. Also, do let us know in the Slack or on GitHub or in the comments if you want to see these kind of live streams more often, if you want to see other content, what kind of content you want to see, right? Want to have specific demos on parts of Tracee, right? Let us know, and I'm gonna get the team to make that. So awesome.
I can
Here.
just mention another
Yeah.
another nice thing. If someone wants to look into more about how to integrate Tracee into their communication systems, however they want to consume the output of Tracee. So in the documentation under integrations, and sorry for not sharing the website, it's also on the website of the documentation, just VS Code is already shared here, so it's easier like this. There is this page about integrations, and basically you can tell Tracee to send all of its detections on a webhook to a webhook. Sorry, you give it the address of the webhook. You can formulate the output using a Go template, and we provide a few Go templates out of the box that you can actually choose from. Or if you just want to send it as a JSON, you can just use the raw JSON template. And oops, where did I go? Just a sec, let's return here. Yeah, all right. And as an example, you have here an example of how to run Tracee and look at the detection as raw JSON, which you could, I don't know, do whatever you want with this raw JSON. And we have examples of how to run Tracee with some very common webhook receivers. These are like projects which are standing up a web server that receives, that listens on an endpoint. You tell Tracee to send to these projects. For example, Falco Sidekick is one of those projects. And you can configure it to send the event into Slack, SMS, open a Jira ticket, or whatever. So we provide a few examples here. One is with Falco Sidekick, which is very common. The other is with Posty, which is an Aqua project that does something very similar. And you can have an example here. For example, here I'm running a Falco Sidekick, Docker run Falco Sidekick. I give it my Slack webhook URL, which I generated from Slack. Anything sent here will post a message to a particular channel in Slack. And I also run Tracee, and this time I Docker run Tracee, but I tell it to send send the detections into this URL again, to this URL, which is basically that container which I just started, and to format the output as just Falco Sidekick. And we provide this template out of the box. You can just copy these examples and experiment with it. But if you just want to deploy it, for example, in Kubernetes, we also provide these examples, these Kubernetes YAML files for which actually stand up Falco Sidekick or Posty and Tracee in Kubernetes, and they are already kind of connected, so you can start using it like this. Basically, what I'm telling you, it's go read the documentation, because if you want to go started, it's pretty much
Go to the docs, check it out.
Yeah.
Can you just, in 2 sentences, tell us what Posty is, since you mentioned it several times right now?
Yeah, so it's basically a tool that helps you manage your security alerts. You can send messages to it. It's a web server, and you can send messages to it, and you can define routes for how you want to handle different kinds of messages. For example, you can say, if I get a message from Tracee, send it to this Slack channel. If I get any kind of high severity alert, I don't care where from, then send a PagerDuty. And it has a lot of different integrations, and it's very flexible. This is what's unique about it. You can transform the incoming alert and form messages on the fly. It's pretty flexible, and you can do a lot of stuff with Posty for reacting to security alerts.
Awesome. Let me add everybody back to the stream. So, great. Anything else? We are already completely over time, which is amazing, because it means that we had lots of interesting things to talk about, and I'm sure we're going to have more of these live streams or similar content. Anything else you want to share in the next minute? Nothing? Grant, Raphael, all good? Awesome.
All good.
So maybe a message to Tracee users, or if you want to get started with Tracee, you go to the GitHub, to the documentation. Anything else that people should check out?
Tell us how you use Tracee. We're really interested.
Tell us how you use it.
How you use Tracee. What would you like to see next? What is missing for you? Even if you're not using Tracee, like, how would you want to use Tracee? We're really interested in that.
Definitely. Let us know in the Slack, in GitHub, in the comments here, anywhere. We're gonna observe all the spaces and see if you have any requirements, anything that you would like to see happen in Tracee. Awesome. Well, thank you so much, everybody, for joining. Thank you for those who are watching either the recording or watching live right now. Thank you, Grant, Raphael, Itai, for joining and answering all of my questions. And all of the questions from the community in the chat. That was amazing. If you have any other questions, join the Slack, comment below. And I hope to see you on one of the upcoming live streams. Awesome.
Thanks, everyone.
Thanks a lot for having me.
Thank you.
Thank you.
Cheers.
Bye-bye, everybody.